Kingsley, Padi, my friend, the Modern Club is ready to listen to you.
Okay. Yeah, thanks once again for that generous introduction. Um, I'm just curious before we start. May I know who MEA is? Is there a full meaning to that?
Okay, I kind of know. Is Martin, Martin Emmanuel Akpalu.
Oh, okay, okay. I
Yeah,
mean, for chemical engineers, when we see MEA, it means a whole lot. So,
mono ethanol man.
okay, okay, all right. Anyway, that's just by the way.
Yeah,
I
sorry,
guess
I was occupied for a short while.
no, it's fine. It's okay.
That's my name.
It's okay. Thanks. Yeah, I guess we can just jump into it. Do we want to use some 5 minutes to probably chit chat
Yes,
about
yeah, we can
general
do that.
stuffs? Yeah. So I don't know if anybody has any question of head before we start with the actual presentations. You're free to ask. For today, I'm your colleague, not a lecturer whatsoever. So just see me as such. Feel free to ask anything that's of your mind. Yeah. Okay. I guess nobody feels like talking. You could also put it in the chat if you're not confident to pick up. You can put your comments, questions, whatever in the chat as well. And but just a quick one. The last I saw on your page, Dr. Bonsu, it seems like you've also roped in Kumasi University, right? Technical
Yeah,
University.
KSTU. Yeah.
Yes, yes, yes. So we have some of those students here as well.
If you're here from
Or not
KSTU,
yet.
it's possible that I don't know if they are here, but yeah, we do have to
Okay.
keep,
Okay, okay. All right. Anyway, we'll chat more about the details later. I think it would be nice to also rope us in from the University of Ghana side.
Ghana,
Yeah.
definitely.
Okay. All right. Okay, cool. Okay, I guess I should just jump into it then. Let me share my screen. Um, uh, okay, since I'm having some technical hitches here. Okay, I hope you can see my screen. Can you all see my screen?
Yes, we can see your screen.
Oh, okay, all right.
Yes, we do.
Okay, okay, thanks. Yeah, I mean, thanks once again, Dr. Bonsu, for putting this webinar together. For me, it's quite a pleasure to share some of the research work we are doing with you guys, especially knowing that some of you are into bioenergy studies and also the modeling club in general. So most of my work borders on both the bioenergy and also simulation studies. So I'm quite happy to share some of the stuff we do with you guys here. But before we dive into this presentation, I'm not sure how many of you are familiar with life cycle assessment. So I took the liberty to sort of give some brief introduction to set the stage for the entire presentation we'll be going through. So to begin with, every product that you see sort of goes through some life cycle. Just like humans, we go through the stage of birth, growing, adulthood, and then eventually end of life. The same applies to all products as well. So for products, we usually have the raw material extraction stage, which could also, in your case of bioenergy studies, it could be even the cultivation of your biomass. That could be the raw material extraction stage. And then we move on to the conversion of this raw material into finished products, which usually happens in a manufacturing facility for most of our chemical engineering products that we know of. That takes place in a manufacturing facility. After this product is produced, we then also distribute and use these products, right? And then eventually we come to the end of life of the products. So for end of life, we're usually talking about end products, like for instance, plastic bottles after you've finished drinking your fruit juice. That becomes an end product in this case here. And we have different ways of handling that end product. In the illustration that I've shown on the slide, we are just looking at a scenario of recycling, but it could also end up being other scenarios like maybe reuse. So in that case, you can just use your plastic bottle to, your fruit juice bottle, for instance, can be used as a water bottle. In that case, you are simply reusing it. Or you can still use it to maybe still drink the same juice again, if your juice is something that you can refill. But then for recycling, you are eventually sort of converting this plastic bottle into another use, for example, plastic chairs. We could also have a scenario where this plastic bottle can end up at a landfill. And that one is like complete disposal. And usually we frown upon that as environmental scientists. We usually don't prefer disposing of things in the landfills because you end up wasting resources and raw materials, so to speak of. So now, what then is life cycle assessments? And here, permit me to refer to life cycle assessments as LCA throughout the presentation, at least for interest of being brief or yeah. So LCA is simply a method that we use to evaluate and analyze the environmental impacts that are associated with products at each stage of the life cycle. So for instance, the raw material extraction, we could actually have some environmental impact there because we are using energy, we're also using chemical fertilizers among others. So some of these could end up being pollutants in your environment at the end of the day. So for each of the stages, we have to evaluate the environmental impacts and then sum it up to become the environmental impact of the product. And that's simply what life cycle assessment does. So the main idea of doing this is to, most of the time, help us identify which stage or phase of the life cycle has the most major impacts, so to speak. So once you identify where your major impacts are, you can then have an idea of how to handle those impacts in a way you would be working towards reducing it, right? And that can also inform how you design your process or how you actually even handle your raw materials in the facility, among others. So that's a brief idea of what the life cycle itself is. Again, there are four main phases of this life cycle assessment. And here we are looking at essentially the first phase, which is usually the goal and scope definition phase. And here we essentially define the purpose of the study or the objective of the study, as well as we draw system boundaries. So for instance, if my objective is to identify which products among two options that I have would give me a lesser environmental impact, whilst at the same time serving the same purpose as the other one, I would have to do something like a life cycle assessment to identify which of them would give me the least impact in terms of environmental performance. And once we come up with that study objective, we have to now define the boundaries within which we want to do the assessment. So these boundaries usually covers the phases of the life cycle we want to look at. In some cases, we might want to limit ourselves to maybe the raw material extraction and then the manufacturing phase only. Or you could actually consider looking at the whole cycle, but this usually depends on the data availability. If you have enough data to be able to do a good enough life cycle assessment, then you can consider the entire thing. But again, as you are all aware, with modeling studies, it's the quality of the work you do depends on what you put in. So if you don't have enough data on some of the phases, you are better off cutting those phases out and looking at only what will be more relevant to your decision making. So the next phase of the LCA is the life cycle inventory. So once you've identified your objective and define your boundary, now you gather the data on the inputs and the outputs for each of the phases that you want to look at. And that's what we are calling the life cycle inventory. So this inventory could actually be in the form of all the materials and energy that goes into each of the phases, as well as the emissions that come out of the phases of your life cycle. So in the case of the manufacturing step, for instance, since you are chemical engineers, you can relate better with that. In the case of the manufacturing step, you have energies going into your process. You also have raw materials going into your process. And you would also have emissions coming from, for example, combustion of, let's say, diesel fuel in your process for your energy supplies. So that emissions would also have to be taken into account as part of your inventories. And then once we identify all this, we then proceed now to perform what we call the impact assessments. So the impact assessment is simply carrying out all the analysis to identify what environmental impacts actually can be associated with each of your inputs and outputs. So in other words, we are actually doing something like an accounting of the environmental impacts of all the inputs and outputs that we have in our entire life cycle. So that's the impact assessment. And this can be quite complicated. So depending on how complex your system or your process is, you may have to do that for a number of inputs and outputs. And due to that, we use softwares to do this type of lifecycle assessments. An example of this software is Stima Pro. So I don't know if any of you is familiar with this, but Stima Pro is one of the common tools that we use for undertaking lifecycle assessment. So in the case of your process models that you use Aspen to do your simulations, we can also use Stima Pro to simulate the lifecycle assessments. And in this environmental impact assessment that we do, we are more interested in environmental impacts like the climate impacts, the terrestrial acidification impacts, and then the freshwater eutrophication impacts. I just want to know by at least a response from one of you if I should explain any of this. I don't know how what familiar you are with any of these impacts I've mentioned so far. Terrestrial acidification impact, and then freshwater eutrophication.
Yeah,
Can somebody tell me?
Yeah,
Yes.
maybe those two, both the terrestrial and the freshwater eutrophication.
I can explain that. Okay. All right. So the terrestrial acidification, I think it will be best to explain it with an example. So for instance, in your process, you have emissions coming from your process. And some of these emissions can be acidic gases like SO2, like CO2, right? And this SO2 and CO2, that forms part of the gases that are emitted from your process. Usually, even in some cases, your flue gas, the compositions will have sulfur dioxide in there. It can also have carbon dioxide in there, right? So these gases, when you emit them into the atmosphere, they can actually react with rainwater, for instance, to become weak acids. For example, weak carbonic acid or weak sulfuric acids. And when that falls back onto the land, when you hear terrestrial, it simply relates to land. So when that falls back onto the surface of the land, it can also harm crops among other biological matter that you can have on the surface of the land. So that's a layman's idea, sort of, in terms of what terrestrial acidification is. And when we talk about freshwater eutrophication, so in that case, it has to do with water, right? As the name implies, fresh water. You may have nutrients which can help algae to grow being washed off from your process into water bodies like your rivers, among others. So for example, you may have, let's say, biological matter in your wastewater, and if you don't treat that fully and you discharge everything into water bodies like rivers, among others, it causes algae to grow effectively because they are getting the nutrient that they need to grow. Meanwhile, your water is actually meant for aquatic life, especially like fishes, among others. So if you have algae growing, it competes with fishes and the other aquatic life for oxygen and other useful stuff that this aquatic life would need to grow. And that's also a negative impact on the environment. So in essence, the processes that we operate in chemical engineering, we also have to take into account the environmental impact that we are having. And this goes beyond the emissions from your flue gases, among others. It can even be quite complicated, including toxic chemicals that could also have impact directly on human health. But for the purpose of this presentation, I will be mainly touching on only these three, whilst focusing more on the climate impact aspects. In the interest of time, yeah. All right. So now the fourth phase of the life cycle assessment is the interpretation phase. And the interpretation phase is usually important because that's the phase where we tend to analyze the results, we draw conclusions, and then we also make informed decisions. You can notice from the figure that all the things, the phases are sort of iterative because you have to be going forth and back between the stages. And this is very important because at the end of the day, you have to double check whether your final conclusions or your answers that you are getting from your model is actually addressing the objective of your study. For instance, so it's an iterative process. It's not just a straightforward process that you begin and end with results. Okay. The next thing I want to highlight here is the fact that I'm not fully aware of how deep you are in terms of the technical aspects of these bioenergy processes. But then I know that presentation I'm going to give now would be getting technical at some stages, especially when I start talking about the bio-based processes and the value chains. But if you are curious to explore the topic further, the full study that I'm going to present today has actually been published in a peer-reviewed open access journal. So you can actually download them for free of charge from online. I've provided a link here, but I would also send it to Dr. Bonso at the end of the presentation. So all of you can actually download it if you're interested in the fine details of my presentation. Okay, so now that we've set the stage for the presentation, and now that I'm also confident that you are all set in terms of the basic understandings of life cycle assessment, I believe we are ready to probably jump into the main presentation at this stage. If anybody has any questions so far, please, you are free to ask now on what I've presented so far before we get into the technical presentation. Okay, all right. Again, you can also be putting your questions into the comment section. I want this to be more of an interacting session rather than a lecture or student-lecture relationship, okay? So if you have comments at some point, you can put it in the comments, and then maybe Dr. Bosu would just raise it up at the end of the presentation. Okay, so now to our main topic of the day. And here I'll mainly be sharing insights into the life cycle environmental impacts of integrating wood chip-based value chains and green hydrogen systems. So in layman's language, we are simply trying to see if we can incorporate green hydrogen into some of the biofuel processes that you're already familiar with, and whether that would come with any environmental benefits compared to the current scenario of having these two systems in isolation or standalone scenarios. I should also add that this work is a result of a collaboration between our team at the Copernicus Institute of Sustainable Development at Utrecht University in the Netherlands, and our colleagues from KTH Royal Institute of Technology in Sweden, as well as our colleagues also from Aalborg University in Denmark. So this was quite a multinational collaboration that resulted in this study that I'm coming to share with you now. Okay, so to give some brief background in terms of the green energy transitions and systems integration, Again, I'm told some of you are already working on green energy, so I would not waste more time there. But I'll give a brief idea of what we mean by the transitions and then the systems integration here. So I believe we are all familiar with the fact that there is a growing concern over the negative impacts from the use of fossil fuels. Some of this impact is climate change. We also have an impact of health in terms of detrimental impact on human health. And of course, the fossil resources are also limited and could actually end up being depleted within the near future. So all these negative impacts are driving a shift to more greener alternatives. And by greener, we are simply referring to renewable or environmentally friendly options of energy streams like wind, like solar, like bioenergy. And among these green energy alternatives, we have what we call the electrolytic hydrogen or the green hydrogen. Electrolytic simply means we are splitting something using electricity. And in this case, we are splitting water to produce hydrogen and oxygen molecules. So how does this become beneficial? This is only beneficial if we are using renewable electricity as the powering source for the splitting of the water into hydrogen and oxygen. In this case, the hydrogen becomes the fuel of interest that can be used in industries and also in the transport sector. The other green energy option that we are all familiar with, of course, is the biofuels. And biofuels, for example, like biomethanol, like biohydrogen, can come from the processing of carbon neutral biomass. I don't know how much details I should give on this, but I believe we'll see more illustrations in the course of the presentation. But the interesting aspect is also the fact that we can actually also integrate this electrolytic or green hydrogen with carbon dioxide that would capture from the biofuel production systems. And this integration can help us to actually produce a third alternative, which we call the synthetic fuel. So in this case, we are using molecules to produce the fuels. An example of this synthetic fuel is synthetic methanol. In some cases, they refer to it as e-methanol, where the E stands for electromethanol. And the advantage of considering this carbon dioxide capture and its integration with the hydrogen for synthetic fuel production is the fact that this CO2 would have been emitted into the atmosphere and it would come with environmental impacts, right? Negative environmental impacts, like your climate impacts. But now we've captured it and we are using it to produce another fuel source. So that sort of maximizes the chances of having a higher environmental impact of our system. But we also have to take into account that we are going to use energy and we are going to use chemicals, among others, to produce this synthetic fuel. So then we also have to take into account the potential environmental impacts from these other raw materials that we introduce into the system. And therefore, the need for doing studies like what we are doing now. So here, we can see a summary of the three main biofuel product systems that we considered in this study. The first one is what we refer to as the advanced biocrude. This biocrude has some traits like the diesel that you know of, the fossil diesel. But in this case, we are getting the biocrude from biomass, so it's a green option. The second product of interest here is the biomethanol. And the third product of interest is the biohydrogen. These three have been selected in the study because of their potentials in terms of their proven technologies and the fact that they are also using a common feedstock, which in this case is the wood chip that we are looking at in our case studies. And then also they have standardized outputs. So why did we consider this? We mainly consider this because we have industries in Europe who have actually developed this to some advanced stages in terms of the developmental stages. They are somewhere within the pilot demonstration phase now, so we can actually gather reliable data from some of their processes for the environmental assessment that we are doing here. Without that, then we can't do a meaningful environmental assessment, because remember I mentioned earlier that the quality of the environmental impact that or the assessments that we come up with depends on how reliable the data is. So if we don't have an existing process that gives us enough information for us to gather good enough data to do a good work, then we can't rely on our results from the simulation we'll be doing. So here we are sort of good to go because we are gathering most of this data from existing industries. One of these companies is known as Torgas, and this is a company based in the Netherlands. So they have developed the two-stage gasification technology. And this gasification technology can also enable us to produce both biohydrogen and biomethanol. The second company is known as Cortus AB, and Cortus AB is situated in Sweden. So they have also come up with what they refer to as the wood roll technology. This wood roll technology simply comprises of a pyrolysis and gasification unit, but it's a technology that is sort of fused together. So there's some technical trademarks in there, which I'm not at liberty to go into the fine details with you guys here. Yeah, but for our biocrude scenario, as you can see, we'll be looking at two process routes. The first one would be simply using electrolytic hydrogen to produce a biocrude. And the second one will try to incorporate synthetic methanol production into the biocrude process. For the biomethanol also, we'll be looking at three process routes. The first one would be a two-stage gasification pathway. And then the second one is the same gasification pathway, but now we are incorporating the electrolytic hydrogen or the green hydrogen. The third one is based on a different route altogether, but that is purely a synthetic methanol pathway that we'll be looking at. For the biohydrogen, we would also be comparing the pyrolysis gasification technology from Cortus AB with that of the two-stage gasification from Torgas. And all this will be compared to a benchmark or a control scenario of a pure electrolytic hydrogen. So in the subsequent slides, I'll be going into the full descriptions just to give you a fair idea of each of the process routes that we've just mentioned. So now let's look at the process descriptions for the three product value chains. And here we are starting with the advanced biocrude fuel system. For the first route, remember I mentioned that we'll be looking at two process routes for the biocrude. For the first route, we consider the hydrothermal liquefaction and a hydrotreating of wood chip technology, which is actually integrated with the electrolytic hydrogen, as you can see in the process block flow diagram. And then for the hydrotreating, we have to feed the hydrogen that we use for the hydrotreating in excess. So we recover the excess hydrogen using a pressure swing adsorption and a membrane separation technology. After this, we recover heat from the gases before we release them into the atmosphere. So the heat that we recover is used within the process. As I mentioned earlier, I will not be going to the fine details because that would take us a lot of time. But then if you want the fine details, you can always download the paper that I just showed you, and you can see the fine details of the process descriptions in there. For the second biocrude route, it's similar to the first one. But then in this second one, we actually also incorporate the carbon capture. So here we're actually capturing the CO2 that we could have emitted into the atmosphere in the scenario one. We are capturing that to use it to produce the synthetic methanol, like I explained earlier. And here we need hydrogen to do that synthetic methanol production from CO2. And the hydrogen here is supplied from the electrolytic hydrogen. That's the green hydrogen. Next is the methanol value chain, where three production routes were explored, as I mentioned earlier. So our route one scenario uses the two-stage gasification technology. And here we also have the hydrogen. Okay, I think I should explain this briefly to give you a good background for your knowledge as well in the bioenergy sector. So here you simply have a gasification process which sort of produces the syngas I'm sure you're all familiar with the fact that gasification leads to syngas production. And in the syngas, the component that are of main interest for subsequent use is the carbon monoxide and then the hydrogen. So in the end, the syngas usually comes with other impurities. It could be tar, it could be soot, it could also be CO2, that's carbon dioxide. So we pretty much clean or purify this syngas, and then we subject it to a process that we usually refer to as the water gas shift reaction. So this water gas shift reaction simply increases the hydrogen content. It takes that hydrogen, it forms the hydrogen from reducing water to hydrogen and then oxidizing your CO to CO2. I know you're a chemical engineer, so I can use these terms loosely in this presentation. But then, so what that means is that you're actually losing your CO that you're interested in, which is the carbon monoxide that you need. You are losing it or converting it into CO2 and obtaining more hydrogen from water in that case, because you have CO2, you have carbon monoxide reacting with water to produce hydrogen and CO2. So that's pretty much the reaction. And this is important because for methanol synthesis reaction, we need about 2:1 ratio of hydrogen to CO for you to synthesize your methanol. So you need to produce more hydrogen, and the syngas doesn't give us that much hydrogen. So we need to use the water gas shift reaction to adjust the hydrogen fraction. And in essence, what this could also mean is that we would have less biomethanol produced at the end of the day, because we are reducing the amount of CO that can be available for the hydrogen production by subjecting it to or converting it to CO2 in the course of producing more hydrogen from your water. So in the second biomethanol process pathway, we decided to now supply our hydrogen from the electrolytic hydrogen or the electrolyzer. So in that case, we don't need to use a water gas shift reactor to reduce our CO amount in order to get more hydrogen, but we simply supply all the hydrogen we need from an external source, which in this case is the electrolytic hydrogen. And this helps us to now produce more biomethanol at the end of the day, because we have all our CO or the carbon monoxide intact for conversion to biomethanol. And the third biomethanol system that we looked at is the synthetic methanol pathway that I mentioned earlier. But here we are using the hydrothermal liquefaction pathway. And in this route, we also use electrolytic hydrogen. But here we are using it in both the hydrotreating. Hydrotreating step, we simply sort of react some bio oil that we obtain from the hydrothermal liquefaction step in order to get impurities out of it, like oxygen among others, so that your oil will be a high calorific oil. If you have more oxygen there, it reduces your energy value or energy availability. I don't know how, okay, I shouldn't say that again, but maybe I should explain that. So your fuel, for you to release energy from the fuel, you simply have to combust it using oxygen, right? And if you have a fuel that comes with more oxygen present in there, it simply means the energy availability will be less. You don't have more carbon and hydrogens that will be combusted to release the energy. So we do the hydrotreating to get rid of some of the oxygen and other impurities using hydrogen, pure hydrogen. So here we are supplying that hydrogen from the water electrolyzer. So it's, in a sense, an electrolytic hydrogen that we are using in there. And we also use the same electrolytic hydrogen to convert the captured CO2 to your methanol. Okay, so now for our third product system, as I mentioned earlier, is the biohydrogen. And here we looked at two technology pathways or routes. The route one employs the Woodrow technology that's developed by the company Cortis AB, as I mentioned earlier. So the technology actually combines pyrolysis and gasification unit operations. And in the second pathway, we have the two-stage gasification technology that was developed by the other company, which is Torgas. So we are comparing these two pathways to hydrogen production. The downstream pathways are almost the same. We usually recover hydrogen from a gas mixture using pressure swing adsorption technology. And again, we also have water gas shift operations to increase your hydrogen fractions from carbon monoxide, because in this case, we are not interested in the carbon monoxide, so we can actually dispense it into more hydrogen production, as I've explained earlier. Okay, so now having identified all these possible pathways by which we can integrate green hydrogen and the biofuel value chains, the question that we want to answer, or the two main questions that we want to answer in this research, are related to the environmental impact of all the scenarios that we've looked at. So the first question here is, which of these biofuel systems or the process integrations can effectively enhance the sustainable production of the biofuels and biohydrogen? So in other words, among all the scenarios we've looked at, which of them can give us a better environmental performance? And the second question that we sought to also answer from this study is the question about how do these biofuels compare to the fossil or the conventional alternatives? So for example, for the drop-in biocrude or the biocrude fuel, you can compare that to the fossil diesel that you use in your cars. And then for the biomethanol, we can compare that to the natural gas-based methanol. And biohydrogen can also be compared to natural gas-based hydrogen or the electrolytic hydrogen. Okay, is there a question? I'm getting some feedback. All right. Okay, so now to the research approach. Our approach essentially involved the use of the LCA tool, and specifically, we looked at a consequential life cycle assessment. So by way of expanding your knowledge on LCA, we have two main LCA methods. The first is consequential and the other is attributional. So consequential simply helps us to identify what the impact of a decision that we are making would be relative to the current scenario that we have. So if, for instance, we are using natural gas-based biomethanol now, and we want to replace it with the natural gas-based methanol, and we want to replace it with biomethanol, what would be the environmental implications? For you to do a study like that, you would have to go by the consequential approach. So just as the name implies, what are the consequences of the decisions that we are going to make relative to the current scenario? And for the attributional, it simply helps us to identify how much environmental impact we can attribute to a specific thing. So for example, if you have, let's say, 100 kilogram of impacts, 100 kilogram CO2 emissions as an impact of an entire system, then maybe parts of that system can contribute, let's say, 20, and the other part can contribute, let's say, 50 kilogram CO2 equivalent to the climate impact. So attributional helps you to now allocate that impact to the various components of your system that you are looking at. So those are the two main types that we have. But for the purpose of our study here, the best option was the consequential, because we are seeking to replace existing fossil fuels or fossil energies. So the geographical scope, we limited it to Western Europe because most of the systems we are looking at are based in Europe. And we also set the temporal scope to the year 2030. Temporal scope here simply refers to the time frame that we are looking at. So we should have at the back of our mind, most often when we are doing these studies, we take into account the development level of the technology. So for these technologies, they are still at the pilot demonstration phases. That means they are not at the commercial phase. So their implementation would not happen within the next, let's say, 1 or 2 years, but probably within the next 5 years time, we can see them coming into effect in terms of commercialization. So we set our model time scope to the year 2030. That means everything that we are going to do has to be projected to that year scenario in the assessment that we are doing. And this helps you to have some forward-thinking assessments so that we always plan ahead rather than doing stuff that have already expired to an extent. We also specified our functional unit, as I explained earlier, as 1 gigajoule of fuel. And if I should break this down, because we are producing different forms of energy, we are producing biohydrogen, biocrude, and biomethanol. But the basis for which we can compare all the scenarios that we are looking at is the energy content of each of these fuels that we are producing. So that's the common basis for which we can compare them. And here we are looking at the common basis of 1 gigajoule of the fuel produced. We also proceeded to gather our life cycle inventory data, which is the materials and energy inputs, as well as the emissions. We obtained those from the pilot plants from the companies, as I mentioned earlier. And for the environmental impacts, we limited our analysis to the climate impact or the global warming potential, and then the terrestrial acidification and the freshwater eutrophication. But in the interest of time, I would touch more on the climate impact or the global warming potential and less on the other two in this particular presentation. Next, like all modeling scenarios, we wouldn't have a complete data to do the models. So there are some basic assumptions that we do here. And also you wouldn't have a complete picture because this is a future scenario, right? So we have to do some assumptions in terms of how the entire system would be like in the near future. So some of the assumptions are what I'm going to elaborate on briefly. So the first is the fact that, okay, so the first diagram you are seeing up there is the feedstock supply chain. By feedstock supply chain, we simply mean where the feedstock is coming from. In this case, it's wood chip coming from forest residues. So how do we obtain the wood chips and how do we transport them to the processing facility for us to convert them into our energy? So that value chain is what you are seeing in the first figure, the figure on top of the slide. So in modeling the feedstock supply chain, we assumed that the wood chip feedstocks would actually come from forest residues, meaning we are not using the wood itself from the forest because that can be allocated to high value uses, like in buildings, among others. But the waste that comes from the lumbering process of the forest wood is what we are using in this process here. And they are presumed to be transported by diesel power trucks in our analysis. This is also very important because we are using diesel, which is a fossil energy, in producing a bioenergy. So you have to actually take all that into account in the total environmental impact assessment that we are doing. Next, okay, here I wouldn't go much into detail, but just so you know, because in some of our processes, we have byproducts, right? Because we are interested in energy, but you can have some byproducts like biochar. If you are looking at gasification systems, it can come with biochar. Some of them can even come with, example, the pyrolysis. You can also have wood ash as a byproduct from that process. But because we are looking at a consequential life cycle assessment, we have to presume that all these byproducts are going to replace some conventional alternatives in the society currently. So for instance, the biochar can replace coal. I'm sure you all know coal. I don't think we have, okay, I'm not sure, but I don't think we have coal in Ghana, but it's quite common in Europe, and I think South Africa also relies heavily on coal. But biochar is similar to coal in terms of the. Sorry, I'm getting a strong feedback. Is there a question?
Yeah, but Gina, so they are we enjoy it. But yeah, China.
Hello, Raouf. I think you are speaking. Please, can you mute? Okay. Can you all hear me?
Yes.
Okay, all right, thanks. Okay, so we pretty much assume all these byproducts are going to replace some conventional products in the society so that we can focus on the core product of interest to us, which is the energy product. In this case, the biomethanol, the biohydrogen, and then the biocrude. So that's what we do here. And I also thought it would be nice to introduce you to this biogenic carbon and biofuels. Yeah, so you are doing a research, most of you are working on bioenergy. And the interest here is the fact that we think bioenergy is supposed to be better than the fossil energy. That's why we are all trying to come up with research that can make it better, can make it cheaper, can make it more environmentally friendly. But if I should ask, do you have any fair idea of why we think the bioenergies are better than the fossil energies? I mean, without even doing any assessment. Why? What is the drive for moving to the bioenergy sector compared to the fossils? Okay, so let me answer that because we are not writing any exams here. Okay, so essentially, if you combust your biofuels, right, you release CO2 or carbon dioxide from the combustion of the biofuels. And this carbon dioxide, when it's emitted into the atmosphere, that's what actually leads to global warming because it's a greenhouse gas. Everybody here knows about global warming, so I'll not go much into details on that. But yes, CO2 is a greenhouse gas when it's released into the atmosphere. It doesn't matter the source of the CO2, whether it is from a bio-based source or it is from a fossil-based source. It will lead to the same greenhouse gas effect. But the reason why we consider the biofuels or the fuels from biomass or bio-based materials to be more advantageous in terms of the climate impact is the fact that the biomass in its cultivation stage, okay, absorbs CO2 during the growth phase through photosynthesis. So in the photosynthesis phase of the biomass, it captures CO2 from the atmosphere in order to grow, and it releases the oxygen that we all breathe in. So this CO2 that is taken out of the environment, we assume balances out the CO2 that is released when we burn the biofuel. I hope that makes sense to everybody here. So it sort of cancels out the effect of the CO2 that will be emitting because it absorbs the same amount and it releases the same amount. Of course, there are some fine details that once we take those into account, the balances can be varying to some extent. But in general, we make that assumption that this can balance out effectively. And that's why biofuel is considered to be better than fossils, because for the fossils, it takes a long period of time for the fossil based raw material, which is the crude oil, to be formed. Some even takes millions of years for the fossil to be formed. So even if the fossil is also capturing carbon into the biological matter that leads to the fossil crude oil formation, it takes a long period to form. So you would end up burning more fuel before you would capture some substantial amounts to convert into the same amount of fuel you've burnt, you are going to burn at the end of the day. So the carbon dioxide emission and the absorption for fossils doesn't balance out easily because it takes a longer period to form than how much we are going to, how the rate at which we are going to release in it. That's why bioenergy or bio-based options are considered to be better in terms of the environmental performance than the fossil. But there is a whole lot of other factors that goes in. I wouldn't go into those details here. And for the electricity, since we are projecting into the year 2030 scenario that this plan to be actually implemented and start operations from the year 2030 onwards, we have to now model the electricity mix of Western Europe for that particular year scenario. So that's more like a projection. And it's a complex model also that we used, but eventually the outcome shows that we can have about 90% of the energy mix that's from their electricity, that's the grid electricity, can have over 90% of the contributions coming from renewables like solar and wind. This is quite developed here currently, but it's not up to the 90%. So over time, they will keep increasing their renewables and they'll be reducing their non-renewable fossils. Okay, so now to the key findings. Like I mentioned earlier, most of the results I'll go into details on would just be limited to the climate impact or the global warming potential in the interest of time. But now let's start with the biocrude process routes. That's the first product value chain that we are interested in. So the results that you are seeing here has the two process routes for the biocrude. Then we have the conventional fossil equivalent for the two processes. So for the route one, which involves the biocrude production with electrolytic hydrogen integration, the main contributors to the climate impact that we observed was the hydrothermal liquefaction and the hydrotreating steps. And this was mainly because they were using catalysts and natural gas-based heating. So to give you a brief context to this, if you're having high temperature heating requirements in your process, like maybe we need to heat, in this case, 400 degrees Celsius. For those type of heat, we can't supply them at the moment with electricity, for example, or renewables at an effective rate, or let's say a cost-effective rate, if I should put it that way. So we'll still be relying on natural gas for those high heats. Again, we also don't have developed technologies for those high heat supplies in industries. We don't have renewable technologies for those high heat supplies. They are still under research. So hopefully from 2030 onwards, we might have some scenarios. But the closest we have now can only handle heats up to 180 degrees Celsius. So if in your process, you are supplying a heat of up to 180 degrees, then you can use the technologies that we call heat pumps. Heat pumps can supply up to the 180, but in our process, most of the heat that we're interested in are 400 and above. So we are still relying on the fossil-based heat supplies. And that's why we are seeing most of the impact coming from the fossil-based heat that we are supplying to the process. Because fossil is dirty, it releases more negative CO2s into the environment. Negative in the sense that they have negative impacts into the environment compared to the bio-based CO2, as I explained earlier. Now, if we turn to the route 2, that's the second biocrude route, we see that because we're in this process, we were integrating methanol into the biocrude system, right? Mind you, the first one was producing only the biocrude, and the second one, we were also producing both biocrude and synthetic methanol using the green hydrogen integration. So in this second route, the electrolytic hydrogen or the electrolytic process to produce the hydrogen was the main contributor to the environmental impact. And this is largely driven by the high electricity demand. For you to produce hydrogen from water using these electrolyzers, you pretty much need a huge amount of electricity. That's why it's important for you to use a renewable electricity. Because if you are using a non-renewable electricity to produce the hydrogen, then it means your hydrogen is not green. In other words, your hydrogen is equally as dirty as the electricity that you use to produce it. So that explains why, because in our case, we had only 90% of our energy mix being renewables. So those 10% which are non-renewables led to this climate impact that we are seeing here for the scenario 2. But then when we compare both biocrude systems, as the route 1 and the route 2, to the conventional fossil diesel pathway, we can see a clear potential for climate impact reduction. So in the results, as you can see, the first two are biocrude. They are way, way less than the other two, which borders on their equivalent fossil options. In summary, the key environmental concerns of these biocrude processes are actually concentrated in their operational phase, mainly through their use of catalysts and then the fossil-based energy inputs as well as the electricity mix. So if you want to have a very clean biocrude in terms of the environmental impact, or a greener biocrude, you would have to supply your thermal energy and your electricity mix using a highly renewable a highly renewable energy option in order to have a greener biocrude. Now let's turn to the biomethanol scenario, where in route 1, which focuses on the gasification-based biomethanol only, the main climate impact actually comes from the feedstock stage. And this is mainly due to the electricity used in the biomass torrefaction and pelletization. In that case, we had to actually pelletize the biomass before gasifying it. And pelletize, as you all know, requires some compaction of your biomass to form pellets. That compaction energy requires electricity. So that's led to that impact that we are seeing there. But then in the route 2, where we're actually incorporating the electrolytic hydrogen to increase the biomethanol yield, we noticed that the methanol production became the main contributor to the emission. And this is mainly due to the high electricity demand in the electrolytic hydrogen production, as well as the mix of the electricity that we were using in that process. In the route 3, which is the synthetic methanol pathway, also using electrolytic hydrogen, the methanol production facility again was the highest in terms of the climate impact. But then we had a byproduct there, which in this case was the biocrude. That's the yellow section in the third bar that you are seeing in your results. So that biocrude byproduct, which wasn't our main product, because in this case, our main product was the biomethanol. So we just obtained this as a byproduct. And if we use that to replace diesel, then it contributes substantially to reducing the overall environmental impact of the scenario 3 that we were looking at. So based on all these findings, we can therefore conclude that while the integration of gasification and electrolytic hydrogen can actually increase the biomethanol yields, you would also have some trade-offs. And in this case, you would have a higher environmental burden, mainly due to the high electricity demand and mix of the electrolyzer that we use to produce the green hydrogen. So if we want to have a greener biomethanol from these technologies, we would also have to supply, we would need a greener electricity supply in order to have a greener biomethanol production. Okay, so to the biohydrogen systems. For the biohydrogen, the feedstock related impact was seen to be higher in the two-stage gasification as compared to the pyrolysis gasification pathway. And this is mainly because in the gasification pathway, we had to pelletize the biomass before gasifying it, as I mentioned earlier. And that pelletization comes with electricity demand. So that's why we were seeing that high impact. Whereas for the pyrolysis, you don't need to torrefy and pelletize your biomass. You can just use the biomass as it is in its raw form. So that explains why we are seeing a higher impact from the feedstock side in the two-stage gasification compared to the pyrolysis gasification. In the results, this can be seen from the two blue sections in the first two columns. But however, when we look at the overall climate performance, we can see for the two, the pyrolysis gasification and the two-stage, that's the first two columns. We can see that the main differentiating factor there is the biochar byproduct credits. So here we were crediting the biochar as a replacement for coal that is used in some of the industries here in Europe. And what this also means is that the one that gives us more biochar in terms of the yield translates into a higher benefit for the process. So here in this case, the two-stage gasification option gave us more biochar yield, which also led to more credits from replacing the coal in society. And also the biohydrogen pathway was seen to perform better than a pure electrolytic hydrogen. But then the main factor here is the electricity mix. So if the electrolytic hydrogen is the one that we are seeing, the purple color, that's the last column, the last bar in the figure that we are seeing. And the main reason here is the fact that if you have a clean electricity supply, then your electrolytic hydrogen, which is a PEM-based hydrogen, will be better because your electricity is green. So the impact that comes from the electricity will be less. Whereas the bio options will now become higher if your electricity is greener. That would be higher than the electrolytic hydrogen. So depending on the nature of your electricity mix, if you have more fossils present, like in the case of Ghana, most of our electricity is coming from fossil thermal plants, like the light crude oil, among others. So in that case, for instance, then we would be forced to go in for the bio-based hydrogen compared to the electrolytic. But if you have a country where their electricity is very green, like most of the electricity is coming from wind or solar, then they might want to look at the electrolytic hydrogen as compared to the bio-based option. So here we are doing a comparative analysis now of the 7 routes. Mind you, our key objective was to find out which of them was the best performing in terms of the environmental impact. So what we did was to simply rank all the processes because we had 7 processes. So we simply want to rank them from 1 to 7. And in this case, the 1 is the least, 1 is the best performing option. In other words, that's the first option. Like they are writing an exam. So 1 is the first option in this case. And then 7 is the worst option in this case. So in this spider chart that we are seeing, the figure that has the least area becomes the best scenario. And the scenario that has the biggest area becomes the worst scenario. So you can see the rankings in the arrow path that I've shown below in the figure. That's the ranking, the order of rankings in decreasing order of environmental performance. So here, when we look at the result, it is quite clear that there are performance trade-offs between the various pathways, biofuel pathways that we're looking at. So for instance, the gasification biomethanol actually comes out ahead in terms of the global warming and the freshwater eutrophication impacts, while the synthetic methanol route performs better in the terrestrial acidification impacts. And also, within the context of our study, that means there could be other factors that if we should take into account, most of what we are saying here would not be the case. But within the context of what we have done, including the assumptions that we made, including the processes that we looked at, and including the companies' data that we used, we can confidently say that the best option for wood chip-based biofuel would be the standalone gasification. That is the gasification without hydrogen integration, without the green hydrogen integration, sorry, and then the base biomethanol as well as the biohydrogen. So in other words, we are better off producing biomethanol and biohydrogen without incorporating the green hydrogen that we were looking at here, simply because our green hydrogen was not as greener as it's supposed to be to make those options better. Okay, so some overall remarks, which is more like a take-home message from the whole presentation. The first is the fact that the integration of synthetic methanol production into the biocrude processes actually has a negative effect on the environmental performance. And the second point is the fact that we see a similar negative performance trend when we try to boost or increase the biomethanol yields by adding the electrolytic hydrogen. And this poor performances was mainly due to the high electricity demand and the mix in the electrolytic hydrogen production. So if your electricity is greener, then maybe the trend will change from what we are seeing here. By greener, we means it has to be, let's say 100% renewable, for instance, for you to see a better performance for these scenarios that we are looking at here. It is also worth noting that all the biofuel systems that we looked at actually outperformed their fossil counterparts when it comes to the climate impact or the global warming potential. So in other words, all the biofuels have a better climate impact than the fossil options. And this goes back to the explanation I gave you earlier, that the bio-based options actually capture CO2 the same amount that they are releasing. So they become like carbon neutral in that sense. And that leads to them having a less impact compared to the fossils. But then if we look at the other environmental impact categories, which is the freshwater eutrophication and then the terrestrial acidification, we see that the results are somewhat mixed. And here, it's mainly because of the electricity mix that we were looking at. So if you have a scenario where you are using a greener electricity mix, and you also replace your diesel transport systems with electrified train systems, for example. So you can transport your biomass using electrified train systems, right? And if you are using green electricity combined with these electrified train transport options, you can actually improve the environmental performances substantially for all the categories that we looked at. So overall, while the idea of integrating electrolytic hydrogen with biofuel production can seem to be appealing, especially in terms of the fact that it can increase your product yield in the case of the biomethanol, or it can also help you to produce more product streams like synthetic fuels and biofuels at the same time. It would only work well if we are actually also using an extremely low impacting renewable electricity as our energy supply for the processes. Okay, at this point, I would like to thank you all for your attention, and I'm happy to take any questions that you may have. But if you have any specific details that you would want to know, I strongly recommend that you consider checking out the paper that we've published for the fine details. My email address is also available in case any of you want to contact me with any comments, suggestions, or discussions whatsoever. I'm open to that as well. All right, thank you.
Well, thank you, Dr. Padi. But maybe what was the first question?
Okay.
Is there a way in which, after we see what is wrong,
Mm-hmm.
since it's already a futuristic process, we use it to, I don't know, generate newer and better designs? Because if it's the future, it means that maybe the design is not even out yet. I guess my question is, can we integrate LCA into design such that as it evolves, so we don't stop at just saying, this is less green, but I don't know, can LCA push us towards greener designs? I think that's my question.
Exactly. Actually, that's the main purpose of LCA. I was just limiting my presentation here to our objectives for this particular study. But there are other studies that we're also looking at, which is actually informing designs in the changes in the technologies themselves. So if I should give you a practical example, you notice I mentioned that for the biomethanol scenario, for instance, we're seeing some benefits coming from the biochar byproduct, right?
Yes.
So if the technology can lead to optimizing the process such that you can have a higher biochar yield, whilst also having a high syngas yield for your conversion to biomethanol, you can actually improve the overall environmental performance. So in that case, it would help you to now focus more on the gasification technology to optimize it to have high biochar yield. Earlier on, they were actually ignoring the biochar and focusing more on just having high syngas, but in this case, they have to now take into account optimization. So yes, LCA can actually help with technology improvements. That's the whole idea of LCA, actually.
Oh, thank you.
Mm.
Please, do you have any questions? Guys, any question?
Dr. Jude, let your students know I'm a student like them. I'm your student. So in this case, they should feel free to interact with me.
Guys, please, let's feel free. Let's feel
Yeah.
free.
I'm a student just like you guys. All of us, Dr. Jude is our boss here. So feel free to interact with me, okay? Let's pretend he's not here and let's have fun.
Hello. Deku, do you want to ask a question?
Okay. I think if there are no questions, then I would ask.
Okay.
Yeah, I mean, this is a general one. I want to know some of the bioenergy processes that they're actually working on. If any of them could relate with any of the things we've presented so far in their individual studies that they are looking at.
Okay, so hey, Martin is not here. So
Okay.
Martin did some work where he kind of compared. It was also biomethanol, but we kind of compared two. So that was much more in the techno phase.
Techno, okay.
Two different gasification technologies.
Okay.
The story there was we went for the straight circulating fluidized bed.
Oh.
And that was because we wanted to go for entrain flow. So entrain flow gasification has a much cleaner syngas.
Yeah.
But to do that, it means that we first had to get char, because char is pulverizable in a way that the other biomass was not pulverizable. So, but that was at the tech phase. I'm thinking maybe the next thing that must follow should be some form of LCA. But that was the techno-economic phase that which one is much more economical.
Okay. Yeah. I mean, that's usually the order. We usually start with the techno-economics first before we go to the LCA. Yeah. Okay. It's good to know that at least somebody can relate with what I've presented so far. I feel like I've thrown everybody off because I'm
Guys,
not
any
getting
question?
any questions. So
Yeah, so I think actually my final year project too is related to
Okay, someone is,
gasification, where we
I think Prince. Please start the question again or the comment.
yeah, I'm saying relating to what the facilitator said. My final year project too is based on the production of formaldehyde from biomass, where we produce the methanol first before we produce the formaldehyde. So
mhm. Oh, okay.
most of the terms is used, I think, is very common.
Okay. I'm happy to know. Yeah, but why formaldehyde? Is there any specific need for formaldehyde? I mean, in Ghana, or
Hello, Prince. Yeah, why formaldehyde?
Okay, so the reason is that most of when methanol is being produced, majority of the methanol is used in formaldehyde production. Even though we have other sources, we can use it as a fuel and use it in other. Mostly the chemical that they use to produce most is formaldehyde. So that's why we focus much on it here.
oh, okay. I mean, in Ghana, do we have a high demand for formaldehyde in Ghana?
Yeah, so the issue is that they don't have any formaldehyde production facility in Ghana here. So they
Okay.
import it. So most of our final projects will focus on the formaldehyde here.
Okay. I'm smiling because when I hear formaldehyde, it's a different use comes to mind. I don't know. We used to hear that it has some high demand in the morgues in Ghana, so I'm not sure. Is that right? I don't know much about
Oh, it
formaldehyde.
can be
Yeah.
true because it can be used as a preservative. So I think
Preservative. Oh, yeah. Yeah. So that's why they use it in the morgue to preserve bodies in some cases. Okay. Okay. That's just by the way.
So, Kingsley, so I gave this presentation at the GHI, the Youth Division.
Okay.
And my contention was, of all the renewables,
Mm-hmm.
the one that we have the highest chance as Ghana to
Yeah.
participate in will be biomass.
Yes.
In terms of, because I don't see anyone developing any electrodes around, but biomass, whether via fermentation or via gasification,
Mm-hmm. Mm-hmm.
I mean, it looks quite relatively simple
Yeah.
compared to
Compared
some
to
of
other
the other stuff. I
technologies.
don't know. I want you to give your opinion on that. That am I onto something there that at least we should focus on biomass first as a country? Because one, we have quite an amount of it, but also we are closer to
Yeah.
that tech than any other thing.
Yes. Yes. It's true. I mean, biomass is quite abundant to us, but in terms of the uses, we also have to exercise some caution, because, as you know, we may end up using it at a faster rate than at the rate at which we are replanting. So if the focus is on, let's say, agricultural residues, for instance, like the corn stover, the corn cobs, and the rest, those ones are inevitable residues. So they are not specifically like dedicated biomass cultivation scenarios. For example, in cases where we are growing energy crops, like in the advanced countries, for us, we should focus more on the residues or the wastes, the biomass waste, rather than the energy crop
The
scenarios.
trees and stuff. Okay.
Yes, yes, yeah. Then we can have a more sustainable case to look at. In terms of the technologies, yes, mostly we tend to quickly run to the options that seem to be fairly simple and easy to implement. And this is mainly due to obvious reasons, because we don't develop the technologies. We always sort of get them from the overseas or the Western countries where they are developing technologies. So we tend to want to focus more on the less complicated options, like biogas production and those options. Those ones are fairly simple to manage. They are not complicated. They don't require a lot of sophisticated monitoring, among others. So yes, those can be easy options to start with. But at the same time, also, we should also take into account the fact that, I mean, we are going global to some extent now. If we have to compete globally, we should also explore the high value products that we can actually get from this biomass. So for instance, like that's why I was happy about the formaldehyde project that this Prince was talking about. Some of these chemicals are quite expensive, right? They are high value. So, and we import them. And yes, the technologies are not that easy to implement, but we can start from somewhere. So I don't believe that we should limit ourselves to the low technologies, the low level, like the biogas production and the rest. Gasification, for example, is fairly simple as well, except we would need some, in terms of the downstream management of the syngas. That's where the challenge is for most of the developing countries. But the gasifier itself, it's not that complicated in terms of implementing it. Pyrolysis also is a fairly simple one. The other driving factor should also be, like I mentioned earlier, the demands, the local demands that we have. We should usually start with what we need, what is in high demand, and what do we import the most. We should focus on those more, and then that would make us to be more sustainable before we start thinking of fancy stuff that's meant for, yeah, exactly. Because they, I mean, for example, in Europe, for instance, they don't have this biomass in abundance like we do. So they treat the biomass like it's gold to them. These residues are actually like gold to them over here. Therefore, they will not dedicate their biomass to low value applications. If they would go for something like biogas, it would come from the waste that they can't do anything with. But they will not use wood, for instance, to produce something like biogas or electricity. No, they would focus more on high value products because the biomass is also relatively expensive to them. In our case, we have it in abundance. That's why maybe we can consider the low value applications. But the moment it becomes quite an expensive commodity, then we may want to actually explore high value applications like the biochemicals, among others. Yeah. So I don't know if I've answered you.
Oh, that's fine. That's
Yeah.
good. Please, any other questions? I promised him that we'll take around 1 hour 30 minutes. So we still have like 10 minutes. Any other comment? Any other question? I can see some of the guys from KSTU. Any other question? Okay, so the other thing I saw is this way can really fit into the Ghana scenario. All this, because we also have all these sawdust coming from all these logging. So there's a way in which, since they are master students who are just now done doing the national service, I feel like there's a way in which they can think about what is the Ghana equivalent of the work that has been done.
That's true. Yeah. I mean, I'm actually open to, I mean, working with some of the students if they so wish, if they want to focus on similar LCA studies for some of the products they are looking at. I'm always open to that. My core area also, as you know, as for Dr. Jude, he knows about that already, but I'm also more of a techno-economic person. Yeah, so Aspen modeling is one of my expertise as well. So if you have any students who are also showing interest in some of these projects, we can always collaborate and manage them. Yeah.
No, thanks a lot. Thanks a lot.
Most
Please,
welcome.
any other questions?
Okay, I feel like Dr. Joe, these your new students, they are not like our time.
Yeah.
Yeah, our time, there's nothing like wrong question or nonsense. No, you just free your mind. That's what I was telling you. I'm a student, so feel free. If you have anything, free your mind. We can chat around. In fact, we can even ask Dr. Joe to excuse us if you guys want.
Please, my question is,
Mm-hmm.
how many countries are embracing the use of biofuel and biomass?
I can't give you a specific number, like maybe 10, 20. I can't give you that, but I can directed to a resource. There is IEA study on that, the International Energy Agency, right? So they have several reports that shows us how the different countries are actually embracing the use of these biofuels. But offhand, in terms of biomethanol and in terms of this biohydrogen, a number of countries have already started them in Europe. So that one I know for a fact that some countries are using it, especially the hydrogen. But the initial phase, they focus more on the electrolytic hydrogen because they have greener electricity from solar and wind. So they were using more of the electrolytic hydrogens in transport systems in industries. Yeah, but I think now with the advancement of the green electricity, they are also trying to see if they can move on to the biohydrogen and the biomethanol. Yeah.
Thanks.
Okay. Okay. All right. If there are no further questions, then maybe I guess we can bring the meeting to an end, right? Dr. Jude, any other thing? Dr. Bonsu, is there any other thing we can talk, or if not, then I think we can end the meeting then, since.
Hello, Dr.
Yes,
Richard.
Chrysler. Yes.
Yes. Thank you very much for
Is your name
speaking.
Chrysler?
Yes, please, that is my actual name.
Okay, good to know.
I get that a lot. It seems Dr. Jude has been occupied a bit. So
It's fine. It's okay.
thank you very much for your time. Really
Okay.
appreciate it. On behalf of the Modern Club and the Department of Chemical Engineering. Thank you very much.
You're most welcome. You're most welcome.
Please, are there any final words you would want to add before we close the meeting?
My final words. Well, I would
Yes,
say
please.
I have been in your situation before as a student as well in the same department. I'm sure Dr. Dakwa is there, right? And
Yeah, Prof. Dakwa, yes.
oh, he's now, yeah, Prof. Dakwa, sorry. And Ankude as well.
Yes.
Okay, great. Yeah, so we've all been in the same seats as you guys. I mean, if you take your studies serious, it could take you to places. And after going out there and studying out there and all that, I realized that we are also doing some great stuffs. So we shouldn't underestimate whatever we are also learning from our department, especially. I think that will be my parting words to you guys. And I'm looking forward to hearing from some of you. My email address will be available. Dr. Bonsu can share that with you guys. If anybody wants to get in touch, discuss anything academic related, I'm available. Okay.
Thank you very
And
much.
I wish you the very best in your individual projects, especially those working on the bioenergy project topics, as well as the modeling or simulation topics as well. I wish you all the very best.
Oh,
Thank
thank
you.
you.
Okay, thanks.
Thank you, guys.
Okay, bye.
Bye.